Hello there, Physics 20s. It's Mr. Jukely again. Today we're going to talk about Unit 5, Lesson 2. We're dealing with horizontal circles, so things that are swung around in a horizontal circle. The circle is level with the floor. Cars that are going around flat circles, like a traffic circle in 98th Ave, like that kind of a thing. So horizontal circles. Let's jump in. Let's have a look. So again, horizontal circles. Notice how this ball, as it whizzes around. Like, guys, I forget what the name of that sport is actually, but whizzes around. It is the ball's motion is parallel to the ground. It's a terrible drawing, is what I'm looking at right now. Sort of the same thing with this guy as he's swinging the bat around in that way. So circular motion that is parallel to the ground. So things that we check out from this and big ideas that we have. So consider this moving in uniform circular motion. This is what we've talked about before. We've talked about AC needs to be towards the center of the circle. We've talked about the speed, or sorry, velocity. There should be an arrow over top of that. That's why I'm confused. The velocity is always at a tangent to the circle, and they have to be 90 degrees to each other, so that that acceleration is not causing the magnitude of the velocity to increase or decrease. It's just deflecting it, and it's always deflecting towards the center of the circle. One thing that I should mention for this is if this is a horizontal surface, we're looking at a top-down view. So it's as if you're looking at the top of a table, and this thing is spinning around on the top of a table. So Newton's second law tells us a couple things. It tells us that the net force always needs to be in the same direction as the acceleration. Cool, so that's not bad. And it also tells us that the net force is the sum of all forces. So F1 plus F2 plus F3. And then finally, it tells us that the net force is the product of mass and acceleration. And even from that, we can get in that acceleration and net force need to be in the same direction. So just kind of putting all three of these pieces together, net force towards the center of the circle. So net force same direction as the acceleration. I gave it away there, didn't I? Which direction does it need to be? Towards the center of the circle. It's going to get messy, so I'm going to make another one, and I'm going to have F net towards the center of the circle. But what we're actually going to do for this is very special for circles. Like this stuff that I've got over here is pretty dang general, right? It's any forces. Special for circles, just like we had a special acceleration, we're going to have a special net force as well. So Fc is the net force for circular motion. So when I say net force and I'm talking about circles, I'm talking about Fc. If I talk about Fc, I'm saying net force, just special for circles. So what we're actually going to do is we're going to say Fc. And then we can expand on this formula just a little tiny bit here. So for circles, we're going to say Fc, or a centripetal force, that's again our net force, is mass times our centripetal acceleration. Cool, okay, so just making it for circles realistically. And then don't forget F net is the sum of all forces. So not just F net, but realistically Fc, if we're talking circles, is the sum of all forces. Cool. So not too different. So what we got to look at for this, and what this lesson is kind of all about, is, well, we have a formula for AC. So how can we make that formula for AC work with forces? And then the other piece that we're looking at for this one, if Fc is just my net force, and my net force is the sum of all the actual external forces, well, what kind of things are causing Fc? So what are those other forces that cause things to go in circles? So that's the big idea. So let's start with the things that cause Fc. So remember, Fc, or net force, is not an actual force. It's just your net force. It's just what's left over. So if I had a car going around in a horizontal circle, that's this particular person right here. The car is going around in a horizontal circle. What is the net force? What is responsible for that car going around in a circle? It's a bit of a tricky question. So here's an easier way to think about it. What is preventing that car from sliding off the track? As soon as we say that sliding, things get a little bit more apparent, I guess. It's friction that is preventing that person from sliding off of the track and keeping them going in a circle. So in this particular case, our FC, our net force, is equal to force of friction. Because there's gravity and stuff, but that's totally out of the plane. That's in the vertical plane. The only thing horizontally that's keeping this person in the circle is our force of friction. What about for the satellite over here? So clearly the satellite is going around in circular motion. There's got to be some force that's responsible for it going in a circle. What force could possibly, because there's no there's no contact between a satellite and Earth, but there's some force there that is attracting that satellite to Earth, keeping it from just flying off into space at a tangent to the circle. Yeah, if you're thinking gravity, in this case, Fc is equal to Fg. Cool. So the centripetal force is the net force, and it's made up of other distinct forces. That's sort of the key with that. One thing that we often see is this myth of centrifugal forces, and I'm sure you have felt this before. So where I typically feel this, I'm sitting in a vehicle, usually when I was younger, so here's me and my brother sitting in the back seat of the car. I don't know how to draw legs for this, so I'm just going to leave it there. And we're sitting in the back seat of the car, and here's the car itself, and the car starts to go around a corner kind of like this. Has your older brother ever leaned into you and squished you, and then you feel like you are squished against the door, against the outside of the car? That's the myth of centrifugal force. It feels like you are being forced to the outside of the car, when in reality, that's not actually what's happening. The car is actually forcing you, so I'm going to call it, what should we call it here? Normal force and friction force, technically. Call it the normal force between the car's door and you are actually pushing you towards the center of the circle, preventing you from flying out of that circular motion. So I hope that makes sense for people, right? So it's actually you trying to leave the circle, your inertia saying, I want to go in a straight line, I want to leave this circle. It's actually the door that's forcing you backwards into the center of the circle. And then what you feel is you're pushing on the door. That's the whole Newton's third law piece. Hopefully that makes sense for people. Cool. So one of the things that I want to get you to go through and check out. So I don't want to steal anybody's videos here, but I do want you to have a look at this. So on YouTube, Google a couple things. We talked about a centrifuge before. A centrifuge is just, in science, it's a thing that spins around really quickly and it separates typically bug components or other things. Lots of astronauts and pilots, well, pretty much all astronauts and pilots, to be honest with you, have to go into human centrifuges. So there are these little things. The pilot sits over here. That's not sitting, but I just told you I don't know how to draw a person sitting. And then this thing whizzes around in a circle. And it goes through and it talks about, you get up to 6 Gs, 9 Gs, 12 Gs is where you start to have permanent damage to your body and stuff like that. So this is like really, and like 9 Gs is where it's really hard not to pass out. So G-lock is when you pass out because blood cannot flow to your brain anymore. So these things are pretty cool. They're what they test astronauts and pilots to make sure that they can have enough G-forces acting on them to fly $1-million planes and spaceships and stuff like that without even without crashing. So I realize I'm talking about this a little bit here. The last thing that I really want to talk about before I say, hey, just go watch these videos, is when we talk about Gs, 1 G is equal to 1 times the acceleration due to gravity, so 9.81 meters per second squared. So that's the acceleration that we look at. If I had 2 Gs, oops, wow, that totally came out backwards and not an eraser. If I had 2 Gs, that's an acceleration that's equal to 2 times the acceleration due to gravity, so 19.62 meters per second squared, which is quite an acceleration due to gravity. Like if you ever jump off a diving board or skydiving or bungee jumping or something like that, it feels like your guts are like dropping right out of your body or coming up into your throat, right? Like it's very uncomfortable even to feel an acceleration of 9.81 meters per second squared. So these people typically go through and do 6, 9 G's, stuff like that, like a crazy amount of acceleration. So 1 G is an acceleration equal to 1 times the acceleration due to gravity. If we were thinking about this a little bit more too, if you had an acceleration of 1 G, that means that the force that in this case, the human centrifuge is putting on you is a force equal to your regular force of gravity. If it's 2 G's, it would be double your force of gravity. If it's 9 G's, you're going to feel a force acting on you that is 9 times your force of gravity, which is why people make awesome faces like this when they're up at high G forces. So anyways, I've been rambling about this for a little bit here. Take a moment, go watch these 3 videos. The first one, I believe, just kind of shows you how it works and shows you a bit of the timing for 6 Gs. The second one goes into a particular process where they're like squeezing their entire bodies, trying not to pass out. So when you squeeze your body, you squeeze your muscles, you squeeze on veins, and the veins push the blood back to your heart and back to your brain. So you see the lady shouting at the guy to do that. And then the last one is where a person intentionally goes into G-lock or intentionally passes out. So they're just relaxing everything, and you kind of see how that looks. So again, put it on pause, go check out the 3 videos. It's pretty entertaining stuff. I'll let you do that now. Cool. All right, we are back, and we have an idea of a human centrifuge. So here is just a little question about our human centrifuge. So I get a 76 kilogram person who's whirled around in a horizontal circle with a diameter of 9 meters. So we've got a mass in that first sentence, and a diameter of 9 meters. One thing that we get out of that, if the diameter is 9 meters, that means that our radius must be 4.5 meters. Cool, okay. Next little piece, it says the centripetal force required for the person to do this is 5.21, so that's FC, 5.21 kilonewtons. I don't really like kilonewtons right off the bat. Let's switch that to 5,210 newtons. We want the time required for 1 revolution. So time required for 1 revolution, that's a definition. Time for required for 1 revolution is period. So what we're actually looking for here is the period. Cool. So let's check this out. Let's see if we can figure out the period for this one. Now, one thing to kind of note is that FC, it doesn't actually tell us what FC is made out of. It's probably just the casing of this thing. So the person sitting in here, they're holding their little control knob. Oh, which, by the way, you saw in the videos, as soon as they release that, so if they pass out or if they're not strong enough to release that, that shuts the whole thing down. So they're squeezing that until they can't anymore. So yeah, this thing's whirling around. It's probably actually the person's seat and stuff that's causing FC, but we don't really need that for this question. So let's go through and let's see if we can figure this out. There's 2 different ways to do this. There's a 1-stepper and a 2-stepper. So the 2-stepper is we know that FC is equal to M times AC. So we know FC, we know M, we should rearrange and solve for AC. So AC is FC, divided by M. Lots of little screw ups here today, but that's okay. We can always get over those. So then FC was the 5,210 newtons, and mass, I believe it was a 76 kilogram person. Go ahead and plug that into your calculator. Cool, I got mine. Turns out to be, let's see, 68.55 meters per second squared. We'll come back to that and we'll talk about G-forces again and see how many G-forces this person has experienced. But anyways, we got this. Now that I've solved for AC, I know that I'm looking for the period. So we have 2 different formulas for our centripetal acceleration. We've got 4 pi squared r over t squared, and we've also got v squared divided by r. Now, which one of those 2 formulas do you think works and makes sense for this? Yeah, if we're looking for the period, it is clearly the one with the period. That being said, you could probably do a 3-stepper, solve for the speed, and then use our speed formula, but that just seems like extra work. So let's go ahead and solve for t. t must be equal to, so I'm going to bring that one up. Well, trade places essentially. So 4 pi squared r over AC, but that's t squared. I don't really want t squared, so I'm going to take the square root of both sides, and that should erase that little 2 right there. That should be good to go. One common question that people ask is, well, should we simplify? Like, I know what the square root of 4 is, and I know what the square root of pi is. Should I simplify? I would say no, if I'm being totally honest with you, because you're just going to plug the numbers in anyways, right? So I'm going to do square root of 4 pi. Please use the pi button on your calculator as well. Times the radius, so that was 4.5 meters. And then we're going to divide that by AC, which we just figured out, 68.55 meters per second squared. Remember that meters per second squared is part of the unit, so you don't actually square anything, whereas the pi squared, that's a number being squared, you actually need to square that in your calculator. So again, take a moment, plug that in, and we'll see what the period is for this. Good, 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 good. I'm ending up with 1.61 seconds, including significant digits. Nice, good, good. So I'll show you 2 things with this now. 2 things. The shorter way, so just kind of do this as side notes. This would be kind of probably the simplest way, but not necessarily the shortest way. The shorter way is to say FC is equal to M times AC, but hold the phone. AC is 4 pi squared r over t squared. So if we just plug that in right where that AC goes, we end up with FC is equal to M 4 pi squared r over t squared. And now it's just rearranging once, plugging in numbers once, but we should still end up with that exact same answer. Cool. So that is that's just another way to do it. The other thing I was going to show people with this one is just a little bit more with that g-force. So if I want to know how many g's this is, right, I'd say, okay, well, 1 g is 9.81 meters per second squared. I need to figure out how many g's are in 68. I just do 68.55 meters per second squared, and I would divide that by 9.81. Let me just get my calculator real quick here. You can do the same. Oh, no, that's totally messed up. I was on a graph for some reason. Must have pushed a button when I put it down. So that is 6.9877. So that is approximately 7 G's that person would be whizzing around with. So you could even go back, because we just saw a video about 6 G's. You could probably go back and time that, and I bet you it's going to be close to a period of about 1.6 seconds. Cool. So anyways, yeah, just putting stuff together. Nice. That was some space for me to work. One of these problems with high acceleration turns is, again, if you get up to like 7, 8, 9 Gs, even the best pilots can't hang on, right? They pass out. The blood can't get back to their brains. So people, and this is actually the University of Toronto, a guy invented this suit that alleviates this problem. And you really don't want to crash a plane, right? It's a person inside of that plane, and then it's like $1 million plane as well. So these were originally just pockets of water throughout the entire suit, arms, legs, you name it. And then when the g-forces got really big, like everything, so say the g-force was really big and the person was accelerating this way, the heaviest stuff and the blood would pool in their legs. But if it's filled with water, it's kind of like wearing rubber boots in a really deep puddle. It squeezes in on your legs and helps squeeze that blood back to the heart and also so it can get to the brain. So it's doing like the squeezing technique that they did, but it's doing it for you. More modern ones have like they're hooked up to pressure and it's air pressure and stuff like that, and you got accelerometers in the airplane and in the suit that tell you when you need it in your legs, when you need it in your arms and stuff. Pretty high tech, pretty neat stuff. Okay, next one that we want to talk about here is, and this is our last example, a car going around a horizontal circle. So there's a race car going around a horizontal circle, radical. What's preventing it from sliding out and crashing? That is absolutely 100% correct. Friction. I don't know how that didn't go to my nice felt pen that I liked. Weird. Okay, so friction. is the thing that is causing my centripetal acceleration in this case. Now, you're absolutely right. There's forces coming out of the page. There's probably some friction going back into the page that's not causing the car to ground in a circle. It's causing it to speed up or slow down. There's also vertical forces. So I got force of gravity, and then preventing the car from going straight through the road is my normal force. And that's kind of important when we're talking about force of friction, because I know my force of friction is mu times Fn, right? And if it's a totally horizontal surface, like we see up here, Fn must be equal to Fg. Nice. Okay, so now I know that I can at least put that in there to help out. Now, the other piece with this is, we talked about, is Fc is equal to force of friction. So again, can you put this all together is sort of our question. And that's the big thing that we're looking at here. So let's check it out. What is the maximum speed the car can go around a corner with a radius of 100 meters if the coefficient of static friction is 0.5? So remember, coefficient of static friction was mu, and our force of friction is equal to mu times Fn. Cool, and this is actually, you get into a bit of math here that when people are designing roads, this is how they come up with speed limits, or one of the ways that they come up with speed limits. So let's check it out. I'm going to start with my free body diagram, same thing that we had before. So I got my force of friction towards the center, I got my normal force and my force of gravity that are balancing each other out. So in the y component, or the vertical component, I've got Fn is equal to Fg, and that's because Fnet is equal to 0. It's not accelerating up or down or anything. And I'm just going to make a little note that's equal to m times g. In my horizontal component, or my x component, here's what we've got. We've got Fc is equal to our friction force. Nice. So the car is asking for our maximum speed. So let's go through and let's start to expand on this, and we'll see if we can find maximum speed. So what I would do is I'd say, oh, well, this is m times ac. Already you might be thinking we're running into a problem. Where's mass in this question? Shoot, man, there's no mass in this question. Oh, that's too bad. I think we'll be able to deal with it, though. I think we'll be able to get through this. And force of friction is mu times Fn. Now, we don't really see speed anywhere in this yet. So a couple different things that we could do. We could solve for AC, and then we could know AC is equal to v squared divided by r, and hey, there's speed right there. Or we could take this, and we could just plug it in, and I think that's what I'm going to do this time. Last time I took more steps. This time I'm going to take a few less steps. So m times v squared over r, where v squared over r is just AC. Now I need to expand on my force of friction one more time. So mu times Fn, well, we know from way back up here, Fn is the same thing as force of gravity, and I know that force of gravity is mass times gravity. So instead of Fn, I'm going to put m times g. Now some of you are going to start to see this where you're like, oh yeah, okay, I see why we don't need mass. So let's rearrange and let's go ahead and let's solve for v squared. So I'm going to divide both sides of the equation by mass, and mass cancels with mass, but hold on, mass also cancels with mass. Nice. Then I multiply both sides of the equation by r cancels with r, and I got a bit of a mess, so I'm just going to rewrite this. I've got v squared is equal to mu g r. Don't really want v squared, so I'll just take the square root of both sides of the equation, so I can get rid of that little guy right there, and all I got to do is plug in numbers. So got to go way back up to see what they were. So I've got 0.5 and 100 meters. So coefficient of friction was 0.5. Gravity is 9.81 meters per second squared, or newtons per coulomb. Sorry, that's physics 30, newtons per kilogram. And then the radius was 100 meters. I really like meters per second squared because look, meters, oh, doesn't cancel. My bad, doesn't cancel. Go back to there. I've got meters times meters divided by seconds squared. So it's meters squared over seconds squared, but then because we're taking the square root of everything, we just end up with meters per second. So again, take a second to plug that into your calculator. I will do the same. I'm ending up with 22 meters per second. Something tells me that it asked for kilometers per hour. No, it didn't ask for kilometers per hour. I don't know why I thought that. Anyways, you could multiply this by 3.6 if you wanted to, and get, what is it there, 78 kilometers per hour. Yeah, so this might have been some math that somebody did on, say, the white mud at some point in time, right? Similar sort of idea. Cool, so that's our lesson for today. A real big recap for this is FC and AC. It's just the net force and the acceleration, but special for circles. They're towards the center of the circle, and FC is made up of a bunch of other different forces. In this case, we talked about two of them. We talked about gravity, we talked about friction force, and then I guess technically normal force with the human centrifuge. So anyways, that's it for now. Please make sure you're doing a bit of practice with this. Do your best with that. And as always, let me know if you need anything. Cool. Bye for now, Physics 20s.